Those Space People, a podcast series of casual cosmic conversations with people working on exciting space projects. Today we have Sanket Suman Dash with us. He is currently an assistant principal engineer for AOCS and GNC at ST Engineering. And ST Engineering is actually Singapore Technologies Engineering, which is a Singaporean multinational technology and engineering group. And his area of expertise, like I said, is AOCS and GNC. And Sanket is currently based in Singapore. Welcome to the podcast.
Hi, Rachna. Thank you for inviting me to the podcast.
So, Sanket, after your bachelor's in aeronautical engineering at Manipal University, right, you went on to pursue masters at ISAE Supero.
Yes,
And then you worked briefly also with a bunch of companies in Europe, and then you moved all the way to Singapore to ST Engineering. So, how did you find this opportunity all the way there, and what made you choose ST?
basically, as a kid, I was always interested in space and stuff. So I always dreamt of building some kind of rockets or satellites, like a lot of kids in my age. And so when I got a chance to do my master's in Supero in France, it was really good learning experience, getting to learn the soft skills and the technical know-how of how to build control systems for satellites and spacecrafts. And then yeah, I was working in Netherlands for couple of companies, but it was in different kind of aerospace domain, like big kites, and doing some navigation algorithms for a couple of startups. But yeah, I was always on the lookout for different space related jobs. And then I saw this profile on ST Engineering, offering this post online somewhere. And then I just tried to find the person's but it was 6 months old post. So I tried to find the person in charge on LinkedIn, and I messaged them that, hey, I'm interested. Do you guys still have the opening? And surprisingly, they still did. And yeah, that's how I ended up in Singapore. Yeah, yeah, that's the entire story.
Wow, that gives you quite a multicultural perspective to space, right? Indian, European, as well as East Asian, or I would say Singaporean perspectives.
Yes, it does. Yeah. So every culture has their own way of thinking, working, and solving problems. But yeah, so it was a very good experience getting to work with, let's say, French people, Dutch people, and then Singaporean people. And yeah, it and every even though everyone has a different style, but everyone wants has the same attitude of trying to solve the problem, for being very focused on that aspect of the job. But yeah, everyone has their own way of approaching it and different based on their own cultures.
So, first of all, before we dive in, right, the terms AOCS and GNC, as far as I know, are often used quite interchangeably. So, is there actually any difference between these two, at least speaking from the satellite perspective?
I would say they are synonyms. So AOCS stands for Attitude and Orbit Control Systems. GNC stands for Guidance, Navigation, and Control. So GNC is more of it's like AOCS is a subset of GNC. We can put it that way. So GNC is more commonly used in NASA and ESA when they talk even about human space flight. So no one uses AOCS when they talk about humans. They always use GNC because there's a person in loop always. Sometime, not always, but sometime to do certain manual tasks, and some portions the automatic control systems take over. So that's what I understand the difference between AOCS and GNCs. But in context of autonomous satellites, LEO satellites, MEO, GEO, it's mostly AOCS. Or in certain systems, it's just ADCS, Active Determination Control Systems, because orbit is naturally controlled by the forces of gravity around the Earth. You're not trying to control the orbit very strictly, and you just let the satellite decay over time. We just control the attitude. Let's say if you want to take some nice photos of the space of Earth using the spacecraft, then you just call, okay, I'm building ADCS system. So yeah, but everything means the same. The algorithms you write, the sensors you use, actuators you use for doing certain jobs are very very similar.
Yeah, that's what I also assumed because when we are explicitly talking about orbit maintenance or otherwise the determination of the orbit, unless one is actively doing some sort of an orbit raising maneuver or other kinds of orbital maneuvers, it's more or less taken care of by physics and gravity.
Yeah, and there are not a lot of like systems right now which are being controlled by humans. There used to be, like going to the Apollo missions and other stuff. Even I think the Crew Dragon missions and of course the Soyuz missions, there are very few subset of missions where there's a person in loop doing certain fine corrections for the spacecraft to dock to the space station or do some other activity. But and of course the space shuttle was the epitome of GNC, where you're trying to use control systems, automatic, and a person in loop who understands how to actually fly the spacecraft, uh, doing their jobs. Yeah, but currently everyone does AOCS or ADCS depending on what their missions are.
So, yeah, so speaking of these different mission types and mission classes, you've primarily worked around small satellites at ST, right? And also in your previous experience.
Yes, around small satellites. So I started off with the CubeSats. So back during bachelor's in India, we had a small team to build a 2 kilo small CubeSat. It was called Parikshit. Parikshit in Hindi stands for tested, and so that's how we came up with the name. And it was a very small CubeSat, and I think we haven't launched it yet, but the main goal of the building the CubeSat was getting hands-on experience for undergrads who had no idea what they're trying to do, but slowly trying to learn certain skills, applying whatever they're studying in theory and practical in the college to real life problem solving on the spacecraft. So that was my first experience doing certain control systems for the CubeSat. And then later on for ST, few years later, I was working on small satellites. First, the Telios 1. Telios stands for Temasek Low Earth Orbiting Satellite 1. So that's a big satellite, about 450 kilos, with a camera on top. And I just joined ST after they had launched the spacecraft already. So I was involved in the in orbit testing and enhancing the performance of the spacecraft over the few years when I was there. And mainly I was also involved in something called Stelios 2. It was a bigger satellite with a big dish on top, a parabolic dish. It is basically a SAR payload, a radar payload which can take photos of Earth in day and night. So that's the project I was involved in from, let's say, from cradle to operations. So I was involved in the design of the project, the testing, building the software, building the hardware, integrating it, and finally launching it and commissioning it in space. So that was a slightly different experience, and it was a very, very enriching experience.
I can totally imagine. I mean, seeing through the entire life cycle of a satellite is absolutely incredible.
Yeah, it is. Yeah, and you get to learn a lot of subtle engineering practices, which you build through experiences. And I was very lucky to have a very good team of people who had already developed two satellites before, Telios 2, Telios 1, and XSat, the first experimental satellite from Singapore. So they knew a lot of things over their experience. And yeah, it was really great to work with them and learn these subtle clues and engineering techniques to help build Telios 2 as well.
Can you talk about the latest advancements and also upcoming developments in satellite GNC, or let's say satellite AOCS?
Upcoming developments. So I can talk a little bit more about the AOCS systems. So previously, AOC systems used to be huge, like because the spacecrafts were huge. So they were primarily used for telecom purposes. So you had this 2,000 kilo spacecraft with huge sensors and huge actuators, huge propulsion units, which used to try to do their job. But since last 20 years, things have got scaled down. But the spacecrafts have got scaled down, but scaling down sensors and actuators takes a lot of engineering because certain things require certain accuracy and certain power, and it's very difficult to extract certain performances out of certain hardware when they're scaled down. So, but I think everyone around the world have been working on that, and that's where the future of AOCS is, scaling down sensors and actuators. So right now we have something we call as reaction wheels and CMGs. These are huge actuators on spacecraft. Generally, like the most famous reaction wheels are on, let's say, Hubble Space Telescope, and they are famous because some of them failed, and when they failed there was actually space shuttle missions which actually flew to replace them. So now these reaction wheels have been scaled down, and in case a reaction wheel fails you cannot again send a space shuttle. So the engineering effort required to build these smaller reaction wheels or smaller, let's say, CMGs, which are control moment gyroscopes, uh, is a lot. and you have to build in really you have to engineer the hardware very precisely and write very robust algorithms so that in case of certain failures you can still get some performance out of it, since yeah, basically that's what is the current way things are going towards. So scaling down of AOCS hardware.
Would you say this miniaturization is making the replacement of these subsystems or these components more difficult?
I'm not sure if it's making it difficult, but I would say it's making it making, let's say, it's easier for downstream applications to build a satellite now, because you have these very accurate sensors and very robust actuators. Then you can come up with certain more scientific payloads or more commercially not viable, but more commercially demanding payloads, which are smaller in size, which you can just launch for a couple of years, do their job, and actually then just deorbit the spacecraft. So miniaturization of sensor actuators actually helps a lot more, and it's contributing a lot more to the what we call the new space segment of the market. So I think it's a good thing, since because there is a market for small satellites and there are rockets now for small satellites. So it makes sense to have sensors and actuators for small satellites as well. But yeah, engineering that is a little bit difficult.
Yeah, absolutely. Miniaturization would greatly reduce the cost of building the satellites, especially when more and more people are using COTS, commercially off the shelf subsystems, to build satellites. And yeah, miniaturization would bring down the power requirements, like you said, and also the weight, further reducing the launch costs. So more people have access to building space systems. That's absolutely true. But the reason why I was asking how miniaturization impacts the replaceability, for example, in bigger missions, is given the context of in-orbit servicing, right? So in-orbit servicing, for example, of course, we're not gonna. I don't think any CubeSat manufacturer is gonna pay or build for in-orbit servicing. But let's say bigger satellites. I mean, Hubble, of course, is the epitome of in-orbit servicing example. But maybe slightly bigger satellites or strategic missions, or I would say 500 kilogram satellites. So in the case of these kind of satellites, how is the miniaturization impacting the design decisions around AOCS from an in-orbit servicing perspective?
I would say it doesn't impact a lot, because it impacts certain, let's say, uh, basic modes of the spacecraft. So let's say if you want to keep the spacecraft in a safe and healthy state, generate enough power, then miniaturization has helped a lot for 500 kilo spacecraft, because you have smaller basic set of sensors like what you mentioned, the commercial off the shelf or COTS sensors and actuators, which can do the job very well. But to fulfill certain mission needs, generally you need the good robust sensors and actuators which have not been miniaturized yet. They're still big, they're still expensive, and yeah, you would need them to fulfill your mission requirements anyhow. But let's say the overall cost of the spacecraft reduces, of course, once you have these COTS components on top. But then again, with the COTS components, since some of these components might be radiation hardened or might not be radiation hardened, depending on what their, let's say, radiation levels, acceptance levels are, uh, it can cause a lot of issues on the spacecraft. So but the good thing is, it depends on the mission. So if your mission lifetime is smaller, then you might have a little bit higher risk appetite to go for a non-radiation hard components. But if your mission lifetime you're looking at for 10 or 15 years, then of course you would like to go for components which have been tested more thoroughly than the commercial off the shelf components.
Yeah, that's very interesting, because in my head I was thinking that the ADCS, the future of ADCS is all going to be miniaturization. But it's very interesting when you say, depending on the mission, you can also go for the classical, the original size components, which will not compromise in terms of functionality, because then perhaps cost of the satellite or weight of the satellite is not really a concern. So this is interesting.
Also it becomes in terms of how, like when you talk about in orbit servicing, it also becomes let's put it in different perspective, it also becomes a cost of point of replaceability. So if you're building a constellation of satellites, maybe you are a little bit more, you can develop a little bit more risk appetite, so you can develop a mission concepts in which multiple satellites in a particular formation can do some interesting missions for you or fulfill a mission requirements. But let's say if you're building one big satellite, which you want to last for a longer time, then maybe you're more willing to buy those expensive components just for the mission requirements, because you know it, you cannot replace it. But if you go for a smaller class of satellites where weight and power becomes a concern, and you know I'm going to launch 4 or 5 of them, then maybe you are more okay to have not very high radiation tolerant space grade components or miniaturized components for mission requirements.
Yeah, yeah, absolutely. I mean, I would not imagine these mega constellations really building their systems for in orbit servicing, right? They would probably go for things like single use fuses on their power system or things like that because they don't care if 10% of their satellites fail.
Yeah. So, like today, I was seeing a video of Astroscale. So, they just launched the ELSA M, let's say, promotion video where they're planning to deorbit one of the OneWeb satellites. So that was that was an eye-opening thing for me. So yeah, so I know Starlink has their own, like, just because of atmospheric drag, they would come down to naturally decay in a couple of years, even if the propulsion system stopped working. But because they're at about 350 to 550 kilometer altitude, but with OneWeb they're at 1200 kilometers up, where the atmospheric drag is very low. So I always wondered what's their business case. And today, watching the announcement from Astroscale, I was very happy that okay, so they actually have collaborated with someone to have a business case of deorbiting their satellites which are not working. So that's really good. So there is some value to not having uh, let's say a very high performance or radiation hardened components if you're going for commercial, if you're going for constellations. And of course, if you're collaborating with other people to help deorbit your spacecraft, then yeah, your replaceability of a spacecraft is not an issue. So you can launch, if one doesn't work, you can launch 3 of them to replace it. So not an issue.
Yeah, absolutely. I only see more and more companies, or let's say geographies or countries, going taking this path as more and more these kind of space law regulations, right? So this kind of space sustainability requirements are built into national space laws. Then more and more, I see more and more companies going taking this path and being more responsible. That's probably good for all of us. Only if there's space, we can build more satellites, right?
Yeah, and with these kind of technologies, always helps to have some other concept. So if you have a satellite which can successfully deorbit other satellites, then you have a concept of rendezvous and docking, which you can in future use to create big space structures, maybe human habitats in future. We never know. So the technology for decaying of spacecraft might be useful for some other use case which we have thought of, or which we may not have thought of yet. So it's always good to have commercial and academic technologies out there.
Now that you mention the inter usability or multi usability of these algorithms, how similar are the usual ADCS algorithms that are present on the satellite to to determine for the daily operations of the satellite versus the algorithms for deorbiting versus, like you mentioned, the algorithms for docking or some sort of in orbit servicing or even tandem flying of satellites or maintaining inter-satellite links. So there is like a lot of these use cases, right? And how do these different algorithms overlap, or how are they different?
I would say that a lot of these algorithms are very classical. So especially if you're building a small satellite, when you're building CubeSats and you're procuring off-the-shelf ADCS components, off-the-shelf ADCS OBC, the onboard computer, which has predefined algorithms, so they are very classical. When I say classical, it means, let's say, when the spacecraft sorry, when the rocket ejects your spacecraft, you are tumbling in space, you're rotating at high body rate, and you want to reduce your body rate. So the classical way to do it is using magnetometers, using magnetometer just to detumble the spacecraft. That's the word we ADCS engineers use. So that algorithm is very widely used by everyone. There's no new algorithm coming up there. Then, of course, for, let's say, for housekeeping operations where you just want to generate solar power, the control algorithms, the estimation algorithms are also classical. You would use accurate representations like Euler angles or quaternions to point somewhere. Yeah, for housekeeping modes, like let's say if you want to track the sun, or you want to track the earth to down to send some data on the ground, you use very basic attitude representations like Euler angles or quaternions and very classical PID control to do that. But when it becomes something specific to your mission, then yeah, then some people might use some advanced control laws, or some old control laws, classical control laws with some new functionalities and some other estimation methods. uh, but overall, for ADCS point of view, things are very uh, well known. The literature is out there, and you can look at how other people have been doing it, and you can tune certain and design certain laws for your particular mission. For rendezvous and docking, or for in orbit servicing, it becomes very challenging. I believe the literature out there is very theoretical right now, and there's not a lot of commercial literature out there. The people doing it, like if, for example, NASA has been doing it for a very long time, but the papers out there are not, let's say, complete. They have certain algorithms, but the implementation of these algorithms are not very well known. So the new commercial companies like Astroscale, maybe D-Orbit, I'm not sure, they have to try out the theory on their own. So there's obviously the pass and fail thing, and then once they figure it out, and maybe they share it with everyone, and then you get to know, okay, these algorithms work, these algorithms don't work. So I would say the literature has been there for last 30, 40 years because of NASA mostly, and later on ESA. So there is not a lot of new things under the table for uh, ADCS and rendezvous and docking. The new things are coming in the orbit side, because right now, like what we're discussing, is people are more worried about collision between different spacecrafts. So that's something very brand new. So there has not been a lot of literature about it, and people writing papers, thesis. They're trying to do certain commercial missions to help deorbit spacecrafts, or to try to determine certain objects in space with a particular accuracy, particular covariances, the measure of the accuracy of the determination. So yeah, that's where the new theoretical knowledge is being digged up by a lot of people around the earth. So that's really good that there's something new obviously trying to do, and we also have some classical methods which have been robust and tested in space.
Okay, wow, that sounds like there's no end to what you can imagine or what kind of use cases people can summon and what kind of research that you can do in this direction.
Yeah, there is not.
It's pretty cool. And what kind of tools and what kind of softwares are usually used by AOCS and GNC teams?
The most, let's say, widely known software is MATLAB. Everyone uses MATLAB because that's what nowadays a lot of kids, including me, we learned GNC through. It is very easy to code where you're not focused on the syntax of what you're coding or how the language is written, but more on the result. MATLAB and Simulink are very commonly used tools nowadays. Apart from that, Python is picking up. So we use a lot of Python back in our office, and I know other people also use it in different commercial companies and research labs. But at the end of the day, if you're writing a code, you have to write it in embedded C. So which I think is your forte, right? If I'm not wrong. So writing code in embedded C, getting it verified by the experts, and also having some idea how to do C++ and C sharp helps. uh, but yeah, at the end of the day, for AOCS engineers, as long as your logic is sound, then writing it in different languages is not of a big deal, especially if you have a team who can help you verify in a particular language you're writing in. You might not write everything perfectly, but as long as what you write compiles, you get some expert advice on how to make it more optimized, then of course, then you write a very good AOCs algorithms in embedded C, and yeah, then you fly it and it works in space. So that's how it works out nowadays.
So, what's a typical career path for an AOCS or a GNC engineer on the satellite front?
Career path would be like you start out by just learning. So if you're in your bachelor's or master's, you try to pick up certain first principles. So you have control theory nowadays in your bachelor's if you're doing aeronautical or mechanical, electrical. You try to understand the basics, When you specialize, you go for GNC or something like that. And of course, when you start off in a commercial company, then it becomes you start off from a junior engineer. Then slowly, as you pick up some experience, go to senior roles. But what happens is when you start with junior, you're still, what I felt, you're still applying a lot of the theory you have learned back in your school to what you're building. But as you become senior, apart from applying your knowledge, it becomes a very cross disciplinary thing. You need to talk to a lot of people. You need to talk to the mechanical team who can help you fit your procure sensor actuators or build sensor actuators in the spacecraft, the EPS team to know that okay, your modules are not going to create some unnecessary issue and burn the entire system. You need to talk to the integration team. You need to talk to every OBC team to get a particular controller frequency out, uh, to control the timing of your let's say, sensors actuators very well, so that your algorithms work very well. So you have to talk to a lot of people, you have to collaborate. So as the more senior you become, you become by default a system engineer, where you need to talk to people, understand how other people work, how your system can help meet everyone's requirements. Because the sad thing about, or not the sad thing, but the most challenging thing about AOCS is that most of its sensor actuators cannot be tested on ground. So you can write fancy algorithms, you can build simulators, you can build hardware in loop simulators, but till the time your spacecraft is up there in a zero gravity environment, you do not know if your torque on the spacecraft is enough to rotate the spacecraft or not. Of course, you can do a best guess estimate, and as you build more spacecraft, you have more confidence that okay, this is the way it's going to work. But when it works for the first time, it's a very good feeling. And yeah, so to get to that stage, you need everyone's help. You cannot do it all alone. As a writing algorithms, of course, you can build up your own knowledge, be very specific. But yeah, if you want to build a complete AOCS system, the I would say a main skill is to talk to and to collaborate with everyone to get your algorithms actually working in space. So yeah, one kind of path. Yeah.
Yeah, I totally get that because most of the systems engineers we see have started off as ADCS or GNC engineers. So it seems like a perfect starting point for them to launch into systems engineering.
Yep, yep, yeah. You get to, because you get to decide, or not decide, but at least write requirements down from the concept of operations. That, okay, this it's going to be detumbling, you're going to be housekeeping, because the first few days after launch is all the ADCS show. You don't care about the image. You just care that okay, the spacecraft is generating power, it's safe, it's in a very controlled environment, it's in the correct orbit. Once everything is ready, then you start taking images or start doing your scientific missions. So the first few days are very intense. So to get it working, you need to collaborate, you need to understand how the entire system could work. So yeah, this is one of the career paths for AOCS GNC engineer. And the other one is on the research side, because there are always really good problems to solve. So if you're more into physics and maths, then you go on the research side. You do a PhD, become a prof, you learn from other students, other profs, and you teach other students, and you build up on the existing literature already available and come up with some new ideas. And the field is very vast, and space nowadays is not just a very s- small space, if I may say. There's a lot of collaboration right now with aeronautics in the commercial sector. Let's say now we have a small UAV flying in Mars. 20 years, 10 years back, I'm pretty sure NASA was just thinking about it. So now it's actually happening. So there's a lot of interactions already between robotics and space and UAVs. You never know, in future you would have big power stations in Mars, or on the moon. So then there are a lot of different kinds of problems you would like to solve. Let's say you have a distributed power supply for all our houses here on Earth. How would you do it on moon if you have a moon base? That's a completely different problem to solve. So a research line is also very interesting, where you're trying to solve problems for the space segment. Let's say you want to try to find out on moon. Let's say you want to drive a rover, which NASA did I don't know, some years, dozen of years back. So if you want to do that, what kind of technologies you need? Can you build it? And maybe in future you would be a part of the private. Now there's a lot of private space missions which fly these rovers to moon, and yeah, maybe your rover is actually going on the moon somewhere in next 5 to 10 years.
You mentioned two kinds of career paths, right? So the second one is the research based career path. Of course, it needs a master's degree and then an eventual PhD or perhaps a few postdocs. But the first path, which is working with in companies as part of satellite teams building satellites, does that career path also require a master's degree or is an undergrad degree sufficient?
I would say it's very different from where you're coming from. Let's say if you're in India now, right now, there's not a lot of focus on control systems in your undergrad. So it's better to get a master's degree, or if you get to do a lot of projects. Let's say you do a lot of you start small. You start up with robots. Let's say you're building a small robots with four wheels. That itself is a small, nice. You build something on your own. So if you have some prior knowledge and some good experience building robots and stuff, you can go into the field. There are a lot of private companies in India already who are trying to get undergrad students as interns, teach them, get some expertise out of them, and help build spacecrafts. So something which we could not do 6 7 years back. There was no private companies in India except a couple of big companies. So but I would still suggest to get a master's degree because that teaches you certain ways of teaches you certain things in depth. And let's say at your master's degree, it need not be in space. It can also be in controls because if you go to France, you go to other countries in Europe, or you go to US, they have actually done control systems for spacecraft aeronautical vehicles. So when the professors are teaching you, they're teaching you something which has already been done. Some of the algorithms have already been tested. So that's real life knowledge you get to learn. And good to build your intuition slowly during a master's on that. So it's good to learn the control theory in depth, but of course, you need not do that. You can always build stuff. You can be on the engineering side of it, not just on the algorithm side.
Yeah, I completely agree with you. I also keep advising people to pursue what I call generic masters, like you said, control systems or, embedded systems or these generic areas, because a lot of times the space centric master degrees kind of water down the core engineering concepts and focus a bit too much on the space aspects, which you will anyways pick up when you work at a space company.
Yes, I completely agree with you. Yeah. So it's good to do that if you are already, let's say, if you want to switch fields, if you have done few years of automotive controls and you want to go to space side, so you do a space course just to understand, oh, this is how the entire process works. These are subsystems, blah, blah. And then you can switch your skill set from automotive controls to, let's say, space controls. But if you're fresh undergrad, I would always say put your time in learning the theory very well, whichever field you have chosen to be. And nowadays, there's Coursera. There's a lot of other uh, tools out on YouTube, a lot of lectures out on YouTube. So as long as you can learn certain things, get your theory right, your first principles correct, which is a learning experience for entire life, because there are always new things to solve, new things to think about. It's always good.
Yeah, absolutely. Now, looking a bit into the future, right? How do you see Chat GPT or any kind of these AI tools in ADCS and GNC?
Oh, it's a very good tool, I would say. uh, the way so me and my friends, actually friends and colleagues, we tried out certain experiments with ChatGPT, and we asked them to estimate certain, let's say, delta V's. We gave a problem to solve, and they fortunately it could not do that. And if you tell it it'll, let's say if it says, oh, the delta V required is 2 kilometer per second or something, and then you say, oh no, this is not the correct answer. The answer is 6 kilometer per second. Then the next answer will be 6 kilometer per second. So it cannot, thankfully, it cannot do our jobs yet. It'll just throw back whatever information you're putting it. But I still feel it's quite useful for writing code. So let's say there's a lot of code which you would like to build, especially if you're doing a master thesis or let's say doing a PhD. Let's say you're writing a big program to control a robot. So if you want to control a robot, you would need to write certain small functions which are already available online. So you can ask ChatGPT to write it for you, and it will write it for you, and then you can build up that code and actually write the main algorithm which utilizes these small blocks of functions to do your thesis. But of course, this the only drawback of this is you will never learn how to write the small pieces of code. And these small pieces of code are essential to understand the physics behind how a certain thing works. So I would say it's really useful depending on what kind of applications you have. I have heard people saying for AI ML applications it's great, but I honestly have no idea how it is great for AI ML applications. But I feel it's really good to generate documentation. Some things, if you don't want to write down, you can ask it to write a very nice report for you and then edit it. At least give you a very big format and fill up the blanks by yourself. But personally, I don't like using ChatGPT to do that. But I know some other people do. Uh, so yeah, it's a I would say it's a personal choice of what profession you are in and what's your personal take on writing documents, writing code. But I think there's a very famous case. Some Samsung engineers or someone wrote asked ChatGPT to write some code for them. If I'm not wrong, was it Samsung or some other company in South Korea? And they actually by mistakenly leaked some sensitive information of the company in the chat gpt. But the problem is and obviously no one can do anything about it because it's somewhere in some server it's somewhere in I don't know which part of the world it is. So there was this very famous case where I think the company said that, hey, please don't use ChatGPT to write code.
Yeah, you're right. I just looked it up. It's Samsung engineers. They were busted because they pasted, like you said, proprietary code. And now the company is limiting each employee to 1024 bytes.
I actually I'm something that's something I would like to discover how the it would be really good to know if there's a lot more usefulness out of ChatGPT in future. I would say it is useful for, let's say, not space applications, but for, let's say, helping people. Let's say, instead of when you give a call to certain hotlines, you get an automated message, which is not very personal to help you solve the problem. But if you have a robot or AI like ChatGPT, it could actually help you solve some problems for healthcare industry or for, let's say, a phone and banking system. Maybe that's where it's useful. But for space, I would say not so much currently.
Maybe not the hard tech, but perhaps I can totally imagine, writing proposals, for example, or writing a lot of content creation. But of course, at the end of the day, anything that comes out of ChatGPT has to be vetted by an expert. So you're right. I also shared your relief, I would say, that it's not yet ready to replace us. But who knows? Today's sci-fi is tomorrow's reality. Let's see. Cool. So you've shared a lot of very interesting insights into how this whole ADCS, AOCS, or GNC, however we call it, all this works on the satellite front, Sanket. And if space enthusiasts or young professionals want to reach out to you, what's the best way to do so?
I would say just by LinkedIn. So I can share my LinkedIn details with the podcast in the podcast description link somewhere. And yeah, just ping me on LinkedIn. I'm open to any conversation. Anyone needs help with something, yeah, I'm open to help out people as well.
That's great. It's been a super fun conversation. I've learned so many things as always whenever I speak with you. Thank you so much for your time today.
No problem. Thank you so much, Rachna. It was really nice to talk to you as well. Thank you for inviting me to this podcast. It's always good to share some stuff.